Well, we have talked about important vector fields of physics in the previous presentation, such as the electric field, magnetic field, as well as the fields that are generated by fluid flows. The one question that we didn't answer in the previous presentation is, how do we actually know that a field is there? And technically, yeah, we could say that that is certainly something that is in the realm of physics, because physics, of course, lives and dies by things that can be measured. But, well, let's think about it a little bit more. How do you really measure, how do you really detect a vector field? And you detect these fields through their interaction between with objects that are in the field. And typically these interactions come through forces. The electrostatic field exerts forces on charges that are being put in the electrostatic field. The magnetic field exerts a force on permanent magnets as well as on wires that carry current. And fluid flow fields exert a force on anything that's within their way, even though they are not technically force fields. And so to be put in the right frame of mind for this presentation, even though, as I said, it's not completely correct in all the technical details, it would, however, be quite beneficial to just visualize vector fields simply as force fields, as something that when you have or are a particle at a certain point in space, the vector field simply exerts a certain force on that particle at that position. With that, we will be able to talk about a very nice visualization of how a vector field aggregates along a path, namely the line integral of a vector field is basically just work that is being done by the field or against the field. And that is in fact what we're going to start this presentation with. I need to just put a little disclaimer or slash warning in here, and that is that in many texts actually the line integral of a vector field is defined and presented after the scalar line integral. However, and this is my apology or reason for doing it this way, the line integral of a vector field itself, that is what is most used in physics. That is where we can put a lot of physical relevance. We will also be able to put some physical relevance on the scalar line integral, and we will connect the scalar line integral to the line integral of a vector field. But the deep visualization, the deep understanding that I can hopefully impart in this presentation really comes through the line integral of a vector field. So let's think about what that can be. Let's think about what we would be interested in if we have a particle that moves along a path through a force field. Okay, so what would be the work that is required to move through a force field? That is certainly a natural question to ask, because the gravitational field as well as the electric field really are pretty much force fields, as long as you have particles that will interact with the field, such as masses, which just about anything has mass, and charges, which would interact with the electric field. And so that would mean if we have a particle that moves on a path, as indicated in red here, then this particle would experience a force that is exerted on the particle as it moves along the path. And of course, as soon as a force is exerted on a particle, that force will either accelerate or decelerate the particle, and that means we will either have to expend energy to stay on this path, or we gain energy by continuing on this path, depending on, if you will, whether we're going against the field or with the field, depending on whether we go quote-unquote uphill or quote-unquote downhill, if we go to higher potential, lower potential, and so on, depending on what kind of field you are moving in. Okay, so to compute work, however, we know that work is force times distance, and we have seen in our presentation on vectors that that turns into a dot product between the force vector and the direction vector of motion. And well, once we move along a curve, of course, we no longer have a single direction vector. And so what people then do is that they approximate the path of motion with a polygon, where we now have little pieces in which our particle moves from one point to another point, and where the direction of motion is almost but not quite parallel to the tangential vector that is on this path here. And so then if we put the origin here, then we know that our motion starts at c of a if this is a curve c parameterized by c of t. And then if we are interested in the work that is required to move along a little piece delta c here, well, then we would realize that this little piece delta c is basically coming, is basically traveled by going from the position c of ti minus 1 to c of ti if we have partitioned our time interval that we are traversing here as we are going along this path into intervals from t0 to t1, t1 to t2, and so on all the way through this particular one that we're interested in that goes from time ti minus 1 to ti. And, well, we are still interested, of course, in this little displacement, which is not quite accurate, but we're going to use that as an approximation. If now the force that the particle experiences is the force at the position c of ti minus 1, then again the vector field will also, or the force field, will also change as we continue traversing the path. But the mantra of calculus certainly is that under sufficiently high magnification, the change in the vector field from here to here will not be very large, so the force will be approximately that as we go from here to here. And under sufficiently high magnification, as long as this curve is differentiable, the displacement along the curve will also be approximately the displacement along this vector, which we can also see already here because the difference isn't that much. And, well, what would that mean? That would mean that the work required to traverse this little piece delta c here is actually delta w, delta work, is approximately force at the starting point times the displacement with a dot product being the times. And yeah, that is of course what we already knew from vectors, right? This is that work is force dot displacement. And we can write that out a little bit differently because the delta c here, and that is something that we have seen in the kinematics portion of our presentations, the delta c is velocity times delta t, right? So the velocity, of course, technically at this point here is tangential to the curve. And so that means velocity times delta t is not quite this vector because it sticks out in this direction, but they are approximately equal. And then the other mantra that we have in calculus, if you will, which is not just a mantra, is that if we make these little time intervals sufficiently small, then these approximate identities really will become equalities, because that's when we will take the limit, and the limit will take care of the various errors that we actually encounter here. So overall, the total amount of work that would be required to move a particle along this red path inside a force field, of which we can only see one representative here, but which is certainly present and exerts a force along the whole path here, that total amount of work is approximately the sum of the little delta wi that we would compute in exactly the fashion that we have computed the little delta w here. So it'll be approximately the sum over all these little time intervals, force at the position that we have at time ti minus 1 times the displacement that we traverse when we go from time ti minus 1 to time ti. And that is just the force at the starting point dot c of ti minus c of ti minus 1, just like we are seeing here, right? If I take c of ti minus 1, traverse that in the backward direction, and then c of ti in the positive direction, which is what this difference does, then that gives us this delta ci that I have also marked here as a delta c. And now we use this approximation that this difference is approximately the velocity at ti minus 1 times the time difference ti minus ti minus 1. The remainder has stayed the same here. And now we're seeing that this is a sum of little differences multiplied with a function that is evaluated at certain points that are related to these differences, because here in this case we can see that this ti minus 1 is this point in time, or this time, as well as this time here, and so that means what we have here is a Riemann sum. And we know what happens to a Riemann sum when we let the little delta t's, the little ti minus 1 go to 0. What happens is that the summation becomes an integral. It becomes what physicists sometimes call a continuous sum from the starting point A to the ending point B of our time interval. We see here this starts at C of A and ends somewhere at C of B. And the ti minus 1, those become our differential time steps dt. And our function, the stuff that we evaluate, that becomes the integrand. So we end up with f of c of t dot c prime of t. And so that means this was what we've just talked our way through here is basically a derivation of why the total amount of work that you have to do if you move a particle through a force field along a path that is parameterized by a function c of t, why that total amount of work is exactly this integral here. So this is actually a derivation. Let's see, this is a prettier way to highlight it. This integral here is actually an integral in this that you can also see and will see in physics, and the derivation was very much a physical derivation. From a mathematical point of view, we can now introduce the following definition. If a vector field f is continuous on a curve C, which is parameterized by c of t, and the parameterization is differentiable, then we can define the line integral of the vector field f along the curve C as the integral of the vector field f dc along the curve C being the integral from a to b f of c of t dot c prime of t dt. You can see here I've done something that I sometimes do, which is I forgot to indicate the parameter domain. Let me do that real quick. And we're back. My apologies again. Certainly we need to specify the parameter domain because otherwise we don't know where to start and where to stop with our measurement of how much, say, work it takes to move along a certain curve in a field. But from the mathematical definition, we can also see that certainly basically what we do is we aggregate the field along the curve, and in some ways then we figure out if the field net goes in the direction of the curve or against the direction of the curve. And for various fields that will then tell us something about the properties of the field and the field strength along these kinds of curves, even though these fields may technically not be force fields. The other thing that then certainly is very nicely demonstrated here is this realization of calculus, that is that integration is a universal tool which allows us to analyze phenomena in which quantities vary using tools that are designed for situations in which these quantities are constant. Because if you want to really remember what the definition of the line integral of a vector field along a curve is, basically it's force times displacement, right? The force is the vector field and velocity times time is the displacement, and what you do then is you integrate. And we have seen that this process of cutting things up into little pieces that we had on the previous panel turns something that technically only works when force and displacement are constants into something where your displacement vector can tilt and your force can also vary over the path of the particle. Other than that, well, okay, yeah, we first want to assure one thing, and that is that if we have a continuous vector field and a curve that is parameterized by differentiable functions c of t with a less than or equal t less than or equal b, and s of u with d less than or equal u less than or equal to e, well then basically the line integral of the vector field along this curve, which is just basically traversed at different velocities at different velocity distributions, if you will, by the parameterizations c of t and s of u, the line integral of this vector field along this curve should only depend on the curve. It should not depend on the parameterization. Basically, even though that feels kind of different, whether I run up the stairs to my office or whether I walk up the stairs to my office, I gain the same amount of potential energy, and all things being equal, if both are done with the same efficiency, I will also expend the same amount of energy going up to my office, even though, of course, running feels a bit more laborious, and I think actually also is, you do expend more energy there, but that has something to do with the biology of how your muscles work. It has nothing to do with the way the physics of the gravitational field works. So basically, you want the line integral of a vector field along a curve to not depend on how fast or how slow you go along the curve. And it turns out that that is indeed the case, because the integral from a to b f of c of t dot c prime of t dt is equal to the integral from d to e f of s of u s prime of u du, and that means this definition of on the previous panel is independent of the parameterizations, and that means we both we have the same amount of work, if you will, either way. The proof has a technical part which we will omit, because basically the crucial part, and that is the part that is really hard to prove, is that there is a differentiable function that maps the interval AB to the interval DE in such a way that C of t is S of G of t, with G of A equals D and G of B equals E. And that's a technical proof that is omitted. Basically, you have to go along the path using the parameterization C, and then going back along the path using the parameterization S, and then using that this composition, which is a rather technical composition then, of course, and reverting things, that will ultimately give you this function G. However, once that is given, the rest of the proof is straight substitution, because if we look at the integral from a to b of f of c of t dot c prime of t dt, well then, by what we have just seen here, that is just integral from a to b f of s of g of t dot s composed with g prime of t dt, and we know the derivative of a composition by chain rule is just s prime of g of t g prime of t dt, and so that means we have the integral from a to b f of s of g of t s prime of g of t g prime of t dt, and we can see that that's now a chain rule, and therefore something that we can do with substitution, because we have g of t plugged into all the functions that g prime is multiplied with, and that means that this is just the integral of f of s of u dot s prime of u du. The substitution is u equals g of t, du dt gives you g prime of t, which means g prime of t dt really is du, and then we also have that g of a is d, and g of b is e, and that means we are okay. If u is g of t, then g of a is d, and g of b is e, and the substitution works out. Okay, well, that was all the technical background as well as the visualization that we have just worked our way through, and certainly now it is time to just think about examples and to visualize what this integral does. So if I take the vector field f of xy being negative yx, and I want to integrate that along the straight line segment from 1, 0 to 0, 1, then technically speaking, this is something that we can do without visualizing anything, because it's straight computation. We will also visualize what's happening, because we certainly always want to understand what the computations do, but let's make sure that we can also simply handle the computations. So the line segment goes from 1, 0 to 0, 1. Well, okay, so we need a line that starts at 1, 0, and we need it to go to 0, 1, which means it needs to go in the direction of the difference between 0, 1 and 1, 0. Well, 0, 1 minus 1, 0 is negative 1, 1, and so the line segment is 1, 0 plus t times negative 1, 1, where t goes from 0 to 1 as it usually does for a line segment that we parameterize this way. Okay, that means that the integral along the curve of f dc is the integral from a to b f of c of t dot c prime of t dt. That's the formula for the line integral. That's something we want to certainly grind into our memory. And the rest is just computation, because basically what that means now is our A is 0, our B is 1. Now we need f of c of t, and that means we have to plug the curve into the vector field. So let's see, the x component of the vector field is negative the y of the curve. So the x component is negative 0 plus t times 1. So the x component is negative t, as we can see here. The y component of the vector field is the x component of the curve that we plug in, which means the y component is 1 plus t times negative 1, which is 1 minus t. Then we need to form the dot product with c prime of t. Well, for a line segment, that is quite simple, because the c prime is just right here. It's this negative 1, 1. And so that's what we form the dot product with. And then, of course, we have the dt at the end. Well, this is something that is easily worked out now. This is the integral from 0 to 1 of negative t times negative 1, which is t, plus 1 minus t times 1, so plus 1 minus t. That's the integral from 0 to 1 of 1, which is just 1. Okay, so the number is 1. What we certainly realize is that 1 is positive, and that's what we want to look at when we look at a visualization of the vector field. The vector field f of xy being negative yx is this counterclockwise spinning vortex. And if we now pretend that this is a force field, then in this force field we want to go from the point 1, 0, which is about here, to the point 0, 1, which is about here. Which means if we do this along a straight line segment, even though certainly the field is never perfectly aligned with our direction of travel, the field is always the direction of travel is always tending to be with the field, right? And that means that if this was a force field, the particle would be accelerated by the field as it moves along this path, and that means that we end up with a positive line integral. So a positive line integral means that the field does work for us as we move along the path. Now we have to be careful here, because these vortices typically occur in fluid flows, and strange as it may sound, in a fluid flow the vortex is not a force field. It is a velocity field, and velocity is not acceleration, right? So we certainly take some liberties here to obtain good visualizations of what the field can do, and typically a field that does work on our particle is a standard and very useful visualization that we can use here to understand what this integral could or should mean. All right, now let's take a look at this vector field again, but let's integrate the vector field f of xy being negative yx first along the straight line segment from 1, 0 to 0, 0, and then along the straight line segment from 0, 0 to 1, 0. So basically, we are traveling still, that should be 0, 1 here, I apologize. Okay, and now it is fixed. We are going along the straight line segment from 0, 0 to 0, 1. So basically, we are traveling in the same field. We are just using a different path. The line segments, well, let's see, how do we encode a line segment? We go from the starting point, which is 1, 0 for the first line segment, and we then multiply by t the difference between the endpoint and the starting point, which would be 0, 0 minus 1, 0, which is negative 1, 0, and that would be the first line segment. The second line segment starts at 0, 0, which we can see right here, and then its direction vector is endpoint minus starting point, which is just 0, 1, as we can see here, so that's pretty easy too. And in each case, we have that our time parameter goes from 0 to 1. Okay, if we want to now integrate this force field along the net path that goes first from 1, 0 to 0, 0, and then from 0, 0 to 0, 1, basically we would integrate first along the first path, and then we add to it the integral along the second path. And as we do that, well, we get the integral from 0 to 1 of vector field with the first parameterization plugged in. Well, in the first parameterization, y is 0, so the x component is 0. In the first path, the x component is 1 minus t, so the y component of the vector field is this 1 minus t here. The derivative is again negative 1, 0. well, not again, but the derivative is negative 1, 0. And then we add to it, well, we need to, for the second path, plug the y component of the second path in here. And so that means because the y component is t, we get a negative t for the x component of the vector field. And the x component of our path is 0, which means the y component of the vector field is 0. And then we have that the derivative throughout is 0, 1. And we can already see that that ends up being 0. The computation is very simple. But certainly now there is something interesting, potentially physically happening here, and that is that as we go first to the origin and then up to our endpoint, our field neither does work nor do we need to do work against the field to travel along this path. And if we were to reverse direction, the same would be true. Physically speaking, of course, we can also see that because our direction of travel is perpendicular to the force that is acting on the particle, and when direction of travel and force are perpendicular, then no work is being done. However, what that means is that if we were to traverse this field first along one side of the triangle and then along the two other sides of the triangle, and if we were to keep doing that, we would gain energy from the field, which is an age-old dream of mankind. Find a field that actually does that, from which we could get a limited source, an unlimited source of energy. That is, as far as physics is concerned, actually a pipe dream, and we will talk about that more carefully in the next presentation when we talk about gradient fields, which are the realistic force fields of nature, and we are going to prove specifically that gradient fields do not have these kinds of vortices, which means this kind of energy gain does not work in gradient fields. Now remember, that does not mean that vortices do not occur in nature, because as a fluid flow, this is a perfectly nice vortex, and from a circular fluid flow, it is also possible to gain energy by traveling around and around. However, what happens then is that you are taking energy out of the field that must be replaced by some other means. So it is, again, not something that creates energy out of a vacuum. It is something that still does not violate the principle of conservation of energy. All right, to finish another technical aspect here, what we have just done is we have taken a line integral and we have pieced it together from several other line integrals. That is actually more common than we might think, coming from calculus, where everything seems to be round and smooth and everything. And so we will call a curve piecewise smooth if and only if there is a continuous parameterization, c of t, where t goes from a to b, and numbers that partition the interval from a to b into intervals t0, t1, t1, t2, all the way through tn minus 1, tn, so that the parameterization is differentiable with a continuous derivative on each interval ti minus 1, ti. So that means that corners are possible because the parameterization can have a different left-sided derivative at ti minus 1 and ti than it has a right-sided derivative. So that means that something like this is useful to parameterize things such as triangles that we just talked about as I discussed the previous example. The line integral of a continuous vector field over a piecewise smooth curve is defined to be line integral f dot dc being just the integral from a to b f of c of t dot c prime of t dt, where the fact that the derivative may not exist at the point ti actually does not matter, because for an integral, individual points at which, or a finite number of points at which the integral is not defined, are insignificant. And in practice, basically what that means is that the integral is actually pieced together from the integrals that we have going from t0 to t1, from t1 to t2, from t2 to t3, and as we have seen in the previous example, sometimes we don't even worry about actually piecing things together in such a way that the intervals are actually consecutive. Sometimes we just integrate the first piece from 0 to 1 with the right parameterization, and the second piece is also parameterized from 0 to 1, and we just add things up. The idea here is that the net work that we get is the same, independent of how we cut this path up, as long as we use legitimate parameterizations. To also show that we have a lot of computational power here and that we can handle stuff that is supremely ugly, let us also take a quick look at the following task. We want to compute the line integral of the vector field f of xyz being negative xy in the negative xy is the same as negative yx, sure. Negative yx in the x component, xz in the y component, and z squared in the z component, along the path c of t being cosine t square root of t e to the 3t, where t goes from 0 to 1. Well, what do? The line integral of f dot dc is just the integral from a to b, so it's the integral from 1 to 2. Now things get hairy because we have to plug this parameterization into f of xyz. That was already pretty hairy with negative yx, because of course x and y were in some way flipped for that field. Well, for this one, it's only going to get worse, but we can do it. We just have to sort it out right. So, for example, the x component will be negative square root of t cosine t. The y component will be cosine t e to the 3t, and the z component will be e to the 3t squared, which ends up being here negative root t cosine t e to the 3t, and e to the 6t, which is e to the 3t quantity squared, dot the derivative of our parameterizations, so dot negative sine of t 1 over 2 root t e to the 3 times e to the 3t, just like we see here, and that is supposed to be integrated against dt. Well, so now we just work out the dot product, so this is the integral from 1 to 2 of root t cosine t sine t, yeah, the two negative signs cancel, everything else is just worked out, times plus cosine t e to the 3t times 1 over 2 root t, times 3e to the 9t, here's where we can do some simplification, dt. And to solve this integral, use a computer, please, really. I mean, this is not something that I would want to touch by hand. I mean, this one's easy. I mean, we know that. This one, I think, may be possible to brute force your way through it somehow, but actually, with the square root, I actually doubt it. I mean, that one and this one here, I don't even want to think about. So, who knows, maybe somebody who's really good with integrals can even crack those, but ultimately, what we're interested in here, if this was a physical problem, ultimately we are interested in the number that this thing gives us, and we are interested in what that number means. And so that means we would certainly want to use a computer here if we just want the number, and the number is 21,883,949.12, and if we think of this as a physical problem, I'm not sure if there's any physical setup where we can get that many accurate digits, so I probably reported too many digits, but so be it. We got us the number. I mean, there's nothing magical here. You just stick that into your computer algebra system. Interpretation, I'm not sure there is a vector field in nature that actually looks like this. This example was deliberately made up to be computationally ugly, of course. A path like this, well, of course, you can brute force that, so that is possible. But what this would tell us is that if there is a vector field or a force field like this in nature, then if we were to travel along this path, we would gain a lot of energy from the field, and we know that from the fact that, well, the number is large and it is positive. So the line integral gives us energy back, if you will. Okay, in terms of notation, because x prime dt is also often denoted by dx, and because y prime dt is also often denoted dy, and z prime dt is denoted dz, well, let's see, what did we have? We had c prime dt, that was dc, and that's because velocity times small time step is a small displacement. So if we look at the x component of the velocity times time, that's a small displacement in the x direction, so that makes sense. If we look at the y component of the velocity and multiply it with a small time step, we get a small displacement in the y direction, so that makes sense too. And then same thing if we look at the z component of the velocity multiplied with a small time step, we get a small displacement in the z direction. So that makes sense. A line integral can therefore be rewritten as integral f dot dc is also simply the integral of writing our vector field as pqr dot x prime y prime z prime dt. That would be the integral from a to b pqr dx dy dz, and then the notation actually is that this is written as integral from a to b p dx plus q dy plus r dz. That notation then, I mean, it drives me a little bit to distraction because I find it a whole lot more natural to talk about these things as dot products force dot velocity or force dot displacement if I include the dt in my term that is the second term in the dot product. This notation, however, is useful in areas such as complex analysis where you literally want to talk about an x displacement and a y displacement, and so overall this is not about a sermon trying to figure out which formula is better. You basically just want to be aware of the various ways in which these kinds of integrals can be written out so that it doesn't throw you off when you encounter these notations. Alright, and that's of course then similar for other dimensions, specifically in 2 dimensions. Of course you don't have the z component, and so you would just have this formula, which is very common actually. And so as long as we remember that dx is x prime dt, dy is y prime dt, and dz is z prime dt, there is no problem for us to compute integrals formulated in this fashion. And when integrals are formulated in this fashion, typically this is what you have to do in order to translate them back to something that you can compute directly. Alright, so now let's talk about the scalar line integral. And a good visualization for the scalar line integral is that we want to compute the mass from a linear density rho. That is a perfectly legitimate physical setup. However, as I said previously, it occurs a whole lot less often than the line integral of a vector field, which is why I wanted us to face that first. So a linear density is, for example, a wire. And if we then want to find out the total mass, well, basically what we will do is we will look at short segments of that wire of length delta c norm. We will see what's up with that in just a second. And we will use those because basically if we look at a linear density, then what we really want to talk about is a parameterization. We really want to talk about a curve. We don't want to think about the fact that this thing has 3-dimensional extent and literally volume at all. We just want to measure mass per length. That is how you declare the density of a wire, for example. Of course, density should ultimately be mass per volume, but for a length of wire, you don't think of that as something that has volume. You think of that as something that just extends along a certain distance, and you want to know density or mass per distance. Okay, so then basically we have again a parameterization that, if you will, runs along the center of the wire, and this parameterization can of course be approximated by a polygon, just like we did in the introduction. And then what we are interested in is the mass of a little piece of length of wire that we have right here of length delta c. And of course, again, if we cut these things sufficiently short, then the density will not vary very much as we go along this particular displacement, and that means we can assume the density is roughly constant. So now we introduce an origin, and basically what we have is along this parameterization that we would have that goes through the center of the wire, we would go from c of ti minus 1 to c of ti. That's this little delta c here. And so then this small amount of mass delta m that is aggregated in this little displacement delta c is approximately the density at the starting point, rho of c of ti minus 1, times the length that we have here. And the length of this little piece of wire, even though it's not quite parallel and even though it's bent a little bit, if we cut these pieces sufficiently short, then that length is about this delta c norm this time around, because we're just talking about a length, we're not talking about a displacement in 3-dimensional space. And that then is of course just density at the point times c prime norm delta t, because delta c itself is still a displacement, and so that displacement is approximately velocity times delta t, right? So it's this c prime times delta t, and if I take the norm of that, then the delta t comes out, and I just take the norm of c prime times delta t to get this approximate length. So the total mass then would of course be the sum of the densities times the little lengths, which would be the sum of the densities at the starting point times c of ti minus c of ti minus 1, because that's of course what I get if I go negatively along c of ti minus 1 and positively along c of ti, then this is exactly this vector delta c here. And that is approximately the density at some point in the density at the starting point times c prime at some point in between times delta t, and that in the limit as we let the delta t's go to 0. This becomes an integral, because this is again a Riemann sum, where I probably should have just said c of ti minus 1 here, c prime of ti minus 1 here also, but in the limit, even with those two different evaluations, that's something where I could have a technical discussion with colleagues in mathematics, but even with that, as long as everything is satisfies the right conditions, such as being continuous, this will converge to an integral where, again, as you make the delta t's in these Riemann sums, quote unquote, short, your delta t's become little dt's, little differentials, your summands become the integrand, and your integral, your summation becomes a continuous sum, becomes an integral from a to b. And so with this motivation that basically says that this type of integral will allow us to compute the total mass of a linearly distributed mass of a linear density, we can define the following. If a function f is continuous on a curve c with parameterization c of t, and the parameterization is differentiable, then we define the scalar line integral of the function f along c as the integral of f dc being the integral from a to b f of c of t times the norm of c prime of t dt, which is exactly what we have seen on the previous panel, only now we call the function f rather than rho. And you can already see I again forgot to specify the domain, which is something that I should certainly do. And we're back, and I have specified, yeah, okay, our piece of wire, if you will, goes from parameter value A to parameter value B. You can already see that here all of a sudden things become very geometric, and when you talk about a wire that just sits there in space, it's a little bit unnatural to think of the t all of a sudden as a time parameter, where we're sort of traversing the wire for no other reason that we need to traverse it for the line integral, even though a dynamic visualization certainly also remains possible. Okay, let's look at an example to just make sure that we can compute the scalar line integral. So we want to compute the line integral of the function f of x and y, being xy, along the positively oriented triangle with vertices 0, 0, 1, 0, and 0, 1. Let me briefly change that. And we're back. Yeah, this is f of x and y. Of course, there certainly is a reason why in multivariable calculus ultimately people drop the arguments. One of them is it's a lot to write, and I think the other one probably is that at least I get it wrong way too often than I want to, or way more often than I would want to. Alright, so positively oriented triangle with vertices 0, 0, 1, 0, and 0, 1. Alright, well, let's draw that. Here's x, here's y, here's the point 0, 0, here's the point 1, 0, and here's the point 0, 1. Positive orientation means counterclockwise, and so that means we want to go from 0, 0 to 1, 0, from 1, 0 to 0, 1, and from 0, 1 back to 0, 0. That means the parameterizations are c1 of t. First curve would go from the starting point 0, 0 to the point 1, 0, so the direction will be 1, 0 minus 0, 0, which is 1, 0. Then we have to go from 1, 0 to 0, 1, so we start at 1, 0, and then travel with direction 0, 1 minus 1, 0, so that would be negative 1, 1. And finally, we go from 0, 1 back to the origin, so we start at 0, 1, and we travel in the direction 0, 0 minus 0, 1, which is 0, negative 1, where 0 smaller equal t smaller equal 1 in each case. Now, technically speaking, if we want to think of this along the lines of an integral along a piecewise smooth curve, then we would want to have a parameterization going from 0 to 1, from 1 to 2, and from 2 to 3. That would just make what we do here a lot more complicated than it needs to be, because we have also seen early on that independent of how we parameterize individual segments, the integral stays the same. So if I had parameterized this thing in 3 segments, where one goes with t from 0 to 1, one with t from 1 to 2, and one with t from 2 to 3, we would still get the same result, and so that means we don't need to make the computation more complicated than it already is. Okay, so that means with C1, C2, and C3 being as indicated on the previous panel, we can now integrate f along C1. And so what would that be? That would be the integral from 0 to 1 of x, which would be t here, times y, which would be 0 for this one, times the length of the direction vector, which is 1 in this case, dt, and of course that length at the end doesn't really matter anymore because anything times 0 is 0, so this integral is 0. For the integral along the second curve, we would get the integral from 0 to 1, again the parameter domain, times of x, which is 1 minus t, times y, which is t in this case, times the length of the direction vector, which is square root of 2, dt, and that gives us square root 2 t minus t squared, and the antiderivative of that is square root of t, square root of 2, antiderivative of t is 1/2 t squared, antiderivative of t squared is 1/3 t cubed, in the boundaries 0 and 1, of course, and so that means that if we compute that, 1/2 minus 1/3 is 1/6, and so this value is 1/6 root 2. The integral along the third curve is the integral from 0 to 1, sure, t goes from 0 to 1 again, x, which is 0, and then really it doesn't matter, but technically y is 1 minus t, and the length of the velocity vector is 1, dt, which gives us 0 also, and that means that the overall integral is the integral over c1 plus the integral over c2 plus the integral over c3, which is 1/6 square root of 2, and that is the line integral here. So if this was something that has density, then it would actually be something very unrealistic, because we're integrating along pieces that have density 0, which basically means that it's not a physical object. Okay, so that leaves us with one more thing, and that is we want to make the connection between the scalar line integral and the line integral of a vector field, because just like we have seen in the previous presentation, that sometimes it is advantageous to separate direction and magnitude in the description of a vector field, it is sometimes also advantageous to actually work out the line integral of a vector field using a scalar line integral. Now that is, I must say, mainly a matter of taste. I will always prefer this one here, but sometimes it's just given in such a way that the scalar line integral makes more sense. Okay, so if a vector field f is continuous on the curve C with parameterization C of t, and the parameterization C is differentiable, and you already see what's missing here again, that seems to be quite consistent. I need to put in my parameter domain, so my apologies, we're going to stop again here, or pause. Okay, so let's take this one from the top one more time. We have a parameterization for the curve C of t with a less than or equal t less than or equal to b. The parameterization is differentiable, and we have a continuous vector field on that curve. Then the line integral on the vector field along the curve C can also be computed with the following formula. It is the integral f dot dc being the vector field, the line integral of the vector field integral along cf dot dc can be computed as the scalar line integral. You see here that in the scalar line integral, the dc doesn't have a vector in it, where we integrate the dot product of the vector field with the tangent vector of the curve as a scalar line integral along the curve. So we also have to say here where t is the unit tangent vector along C, the direction vector. And the proof is pretty simple, because if we take the line integral of the vector field f dot dc, then that is the integral from a to b f of c of t dot c prime of t dt, and c prime is of course nothing but c prime divided by c prime norm times c prime norm. We have done nothing but just multiply by 1 here, and now we can see that f of c of t dot c prime of t divided by c prime of t norm, that is the unit tangent vector. And so that is just the integral from a to b f of c of t dot t of c of t times c prime of t dt, and by the formula for the scalar line integral, that is just the scalar line integral of f dot t dc, and that's it. Alright, so we have familiarized ourselves with line integrals. It should not be a problem to set up and compute line integrals, except for the usual problems that integrals will pose to us, but that is just the nature of the beast. That is something that we know since we first started computing integrals, that can get rather hairy. We have also seen that these line integrals can be interpreted as, for example, the work that is done against a force field, or the work that is done by a field on a particle in the case of the line integral for a vector field. And we have seen that the scalar line integral can be interpreted as computing the mass of a linearly distributed density. And then, of course, the important theorem that connects these two notions together is the one that we have on this panel right here. Alright, well, you've got some thinking to do and you've got some homework to do. We're going to talk about the fundamental theorem of line integrals on the next presentation. Thank you.